Hello and welcome back, everybody. It's good to connect again with you, even though we are in a video format for this lecture. But again, thank you for opening this up and each of the separate groups. So, whether you are a Nevada High School student, dual credit, or you are a Crowder biology student, whether you are a Nevada A&P student, or maybe you are a Crowder A&P student. Welcome. Thank you for watching this with me. Man, we are going to have some tremendous fun today. And not only just having fun during the lecture time, but when we are together in the classroom, the fun and the excitement, at least for me, and hopefully it comes out in all this. But this kind of stuff, you're looking at the screen going, man, that's a lot of stuff. And you're right, it is. But hey, we got a Chief ticket on the screen. Anytime you can have some reference to the Chiefs, that's going to be a great day. And I'll talk about why that is there. But the things that we're going to look at today may seem complex, and what they really are is they're pretty mental. They're pretty high level thinking as far as analyzing the situation. But we're going to break it down into super small chunks and get some good examples. And then when we're in the classroom using the stick and ball chemistry models, we will practice a bunch to make sure that this stuff is understandable, comprehensible, digestible, however you want to say that. But what we're really going to be talking about today, if I could come up with one sentence that would summarize what we're going to be talking about, it's what happens when elements interact with each other, and it's all about the electrons. So anytime you're thinking about anything today, think about what's happening with the electrons, and that will go a long way to helping you to be able to properly analyze and to respond to any situations or prompts that you're asked to do. So with that in mind, again, thank you for joining us, and let's get started. All right, so let me move my mouse pad around here. Sometimes my wife, when I'm not here and she dusts in here, things aren't put back to where they need to be. But anyway, that's a whole different discussion. Let's see. Let's start off with some blue. We got a lot of red with the Chiefs, and I've written in red down here. So let's start off with blue. So we're going to be working with, and I selected an element that has a lot of electrons, just so we can kind of begin to talk about the different parts, and so you can see. But I chose hassium, not for any particular reason. Just when I looked at the periodic table, and excuse me, I wanted to get a full view of everything. I just chose something with a lot of stuff. So hassium is the one I chose. Now, the first thing to recognize is this is an element or an atom that kind of shows everything. Obviously, if you have an element with a much smaller components, it won't have nearly this much nor this many rings. But what we want to talk about is that if an element has enough electrons, then you're going to see all 7 of the rings. 1, 2, 3, 4, 5, 6, 7. Now, if these two, this electron here and this one here wasn't here, you wouldn't see that 7th ring. And I say that because when scientists look at, with super powerful microscopes, look at elements that have fewer electrons, when there isn't, it's like the rings are this invisible force that shows up when the electrons are there. They're always there, but they're not visible, but they're not observable unless the electrons are on there. I guess it's kind of like an electric stream or stream of electricity. If it's just uncontained, you can't see it, but you can certainly see the evidence of it if it's within a cord plugged into an appliance that's plugged properly into the wall that's then turned on. So they're always there, but not necessarily visible unless an electron is on there. So, but 7 rings, and let me close this and just go down to this periodic table here just real quickly, and that correlates to the 7 rows, 1, 2, 3, 4, 5, 6, 7. So that kind of tells you that there's a relationship between the rows of a periodic table and the rings of an electron. So in other words, if the element is in the first row, yeah, the element is in the first row. I had for some reason I paused there. I don't know why, but anyway, if an element is in the first row, then its electrons are going to end on the first ring. If the electron is in the second row, then its electrons will end on the second ring, and third row, third ring, and so on and so on and so on. So bring this back up here, open the pen back up. So 7 rings, 7 rows, and that relationship we just talked about. Now, the idea of what we're going to look at today is the proper placement of electrons as they occur on the atom itself. So when an atom, is being put together, and the electrons are going to their proper place, and they do have a proper place. It'd almost be like if you had a marble collection, and not only did you have a little section for red marbles and blue marbles and white marbles and black marbles, but if the marbles had patterns, like maybe a cat eye pattern, then the red marbles would go in this section, but then there'd be a smaller section for the red cat eye marbles. Or if you had, maybe it's a red-white mix, they got a little bit of white on there. They got a main color and then a little bit of white, and they had a cat eye, then you would have sections for those as well. So it's a pretty organized, and that's what the cheap ticket is here for. When electrons are placed up on a ring, they do go into particular spots, much like if you buy a cheap ticket. Okay, you don't get to set just anywhere you want. Okay, there's a section that you have to go to, and a row that you have to go to, and then a seat that you set in. Okay, electrons are the exact same way. They have a section that they have to go to. Okay, and the section would refer to the ring. Okay, then they have a row or a place that they have to go to. Now, the electrons don't necessarily have a particular seat. They just have to be in the right row in this case. So they only have 2 discerning sections, the right ring and then the right section. And those sections I've got labeled right here, and they help us to determine where they go within that ring. So when someone would say, hey, how many electrons can ring number 4 hold? That's not an easy question to answer, because one, it determines how many electrons that element has, but the bigger question, or I should say the better question is not how many rings can how many electrons can each ring hold, but how many sections does each ring have? But we'll get to that. But first, let's start with the idea of how many electrons can be held within each section. Now, if a ring, let me back up. I'm getting ahead of myself. So on the rings, there is the S section, and the S section can hold 2 electrons, and that's right here. Okay, and then there's a p section, and the p section can hold 6 electrons. And then there's a d section, and that can hold 10, and there's an f section that can hold 14. So you can see that if there is a ring that has all 4, and we can simply add those up, 14, 10, that's 24, 30, 32. So that particular ring could hold up to 32 electrons. Not every ring has all 4 sections, as you're about to see. That section is right over here. Okay, this is a list of the rings and the sections that they hold. So for example, like the first ring has an S section, and that's all it has. So if you look back over here, then the first ring can only hold 2 electrons. Okay, the second ring, if we look over here, has an S and a P section, so it can hold 2 and 6, so 8 electrons. So the second ring can hold up to 8 electrons. The third ring, if we look over here, has an S, P, and a D section. So it can hold 10, 6, and 2, which would be 18. And we keep going down. 4 and 5 have an S, P, D, and F section. So they can hold the entire 32, as we've already mentioned. And then once we get to 6, we lose that F section. Okay, so it can hold 18 because it's 10, 6, and 2, just like number 3. And then 7, just like number 2, holds 8. And it's that 8 that is going to be the focal point of all that's going on. It's that final 8. Because that takes us to, all the way over here, the octet rule. Okay, we can see this prefix oct refers to 8. If it's a geometry class, octagon, that kind of stuff, octopus, 8 legs, so those kind of things. So an element, the octet rule simply states an element will bond with things to try and get a full outer shell. Okay, and in that case, that number is 8. It's trying to get a full outer shell. So that's the octet rule. So let's look at, we're going to look here. This is called a diagonal diagram, and it wouldn't take much reference to see what's called a diagonal diagram. But this is the way that the electrons are placed. If you were in a laboratory setting and you had the protons, neutrons, and electrons, and you were trying to recreate the building of an atom, you would find that the electrons fill themselves into their proper space in this order. Now, how someone came up with this and the powerful equipment that would be needed to observe something like this, I mean, that would be some tremendous, tremendous equipment. But the idea is this is how it is done. What happens first, and the way you read this is that you start at, and I'll put a little X right here, at the back end of the diagonal line and work your way down through the arrow. Okay, then when you get to the end of the arrow, you go to the next diagonal line and read down that diagonal line. Now, as I mentioned in our last video, if you have been in a chemistry class in a high school setting, either you're a current high school student and you've had one, or you are a recent graduate of high school and you've had one, then all of this, hopefully, is just a simple review. And if not simple review, at least when you see these things, you're thinking, oh yeah, I remember, whether it was Miss Branham or whoever you might have had in a chemistry class, I remember all that stuff. So then once you get to the third diagonal line, the 2p section is filled. So that refers to the second ring and the p section within that ring. And then 3s, so it's the third ring and the S section. And then you go to the next diagonal line, the P section, the third ring, and then the S section of the fourth ring. And you may ask yourself, well, we're just going in order here. Why does this need to be some fancy diagonal? Because we get to the point to where they're no longer in order. And I say that, and you can see that right. I'm going to just put it right here. And this pattern will occur the rest of the way. You fill the 3S section, which is the first section on the third ring. And then you come over here and you fill the P section, which is the second section on the third ring. But then you jump to the fourth ring, okay, and fill the S section, and then come back to the third ring to fill the D section. And you may say, whoa, why would the electrons do that? Yeah, that is way beyond the knowledge base that I have. So all I can say is why it does that, no idea. Okay. All I can tell you is that that's how it does it. And when you learn the electron configuration or the arrangement of electrons, this is the pattern that we know that it happens. Okay, then once you do that, and we're not done with the mind-blowing aspect here, the third D, then you go back to the fourth ring and fill the P section, and then you jump to the fifth ring to do the S section, and then back to the fourth ring to do the D section. And you'll notice that over here to the right is the 4F section. So we not only then go back to the fifth ring and then to the sixth ring, and then we come back to the fourth ring to fill the F section. So it's a lot of stuff. And so when we're drawing in class, and I'll do one here as an example, but when we're drawing them in class, we'll do a bunch of them just to help and with the understanding and the comprehension of what's going on here. So we'll draw these and we'll draw these until everybody is satisfied that they have a decent grasp of what's going on. Now, there are a lot of students that this diagram makes a lot of sense to, okay, and they can follow it, and it's not a big deal. There are other students that say, whoa, what in the world are you talking about? So it has just been easier for some students. And what I've done here on this section down here that I'm underlining is I've simply just written them out in order. So what's in this order is the same order as what's up here. It's just written straight out. And for some students, that's easier to follow than the diagram. But either way, you get the same results, the same conclusion, the same endpoint. And so we can work it with either way. So let's just try one. Okay, let's just try one and see, so you can kind of see the building process and how it goes about. So let me close the ink tray and let me move this periodic table up here just a little bit so we can see some of the elements. And I'll get my pen back out and let's go back to the red so they're nice and bright. And we draw the electrons. So if we just pick one at random and we'll say, let's just look at chlorine here. Okay, chlorine has 17 protons. So if it's a balanced atom, which when you're looking at the periodic table, those are balanced atoms, it also means it has 17 electrons. Excuse me there. So 17 electrons. Now we've already identified that since it's in the third row, that the electrons are going to end on the third ring. Now this diagram has 5. I just pulled up with Google a blank electron shell diagram. We could have all 7 if we needed to, but the examples that we draw with and the ones we do in class, we won't have all 7. We won't do one that's that large that that makes you go through the entire process. But I've had many students in the past that want that experience, and hey, you just pick an element that has a lot of the electrons, and you can pick calcium. I even had one student one year who thought this stuff was so cool that they actually sometimes they worked on it in class, other times at home, and it certainly took longer than what we studied it as a material. But eventually, they drew all of the elements individually and had them in their notebook and shared it with me. So that was pretty cool. I mean, most students would be like, "No way!" But anyway, they enjoyed it, so they did it. So you just work with this as much as you want to on your own, but we will spend plenty of time uh, working on them in classes. So back to chlorine. If we take chlorine, so we've got 17 elements to fill. And the way this will work in class is I will definitely encourage you to keep track of how many electrons you've placed, simply just by starting with your beginning number and subtract them out. To me, that's the easiest way not to make a mistake and either have too many or not enough. So, for example, I'm just going to write the number 17 over here. All right, so we know from our diagram, and since I moved this up and the diagonal diagram isn't fully in place, actually, I shouldn't do that. Let me bring it up so I can use both styles, whichever one, no one do that, whichever one that you're planning on using, you can see it fully. All right, now we're back to chlorine, 17 electrons. So our first stop would be to, oh, so I don't have my pen up. That's what it is. All right. Our first stop on the placement tour would be at 1s. And so we're going to be on the first ring in here. And we know that the S section can hold 2 electrons. So we're going to put 1 electron right there. And we're going to put 1 electron right there. Now, when we're working with rings that have multiple sections, the electrons will be more closely placed. But because the first ring only has 1 section, they can go anywhere. And just for aesthetic reasons, they're typically drawn on opposite sides. So we have placed 2 electrons. So I'll mark out the 17. Now I got 15 left. Okay, and we just did this one right here. Okay, our next stop, since we've done with that diagonal, we go to the next one, and we do the 2s section. And again, that's right there, and it's also right here. So we'll go to the second ring, and we're going to place 2 electrons. But because the second ring has 2 sections, we can't place them on opposite ends. So we're just going to place the 2 here together, here at the top. And so we have placed 2, so we'll mark that out, put a 13. Okay, and we have now to do the P section. Okay, so we finished that one, and now we're to our third diagonal. So we're here, and we're also here. Okay, and the P section, as we talked about over here, can hold 6 electrons. We've got 13 left, so we have plenty. So we'll come down here at the bottom, and we'll place 6 electrons. There's 1, 2, 3, 4, 5, 6. And then we'll subtract them so I don't forget. And I got 7 left. Now, when we draw these in class, whatever class you may be, there's no right or wrong as far as where exactly they are. The more sections they have, the more grouping or tightly grouped the sections may need to be. But just for understanding reasons, this is my S section and this is my P section of my second ring. Okay, so now we have finished this one, and then we're going to continue down our diagonal to the 3S. So we're going third ring, S section, and we know S section can hold 2, and we've got 7 left, so we got plenty. So again, we'll go to the third ring, and we'll place 2, and then we'll subtract them. And now I've got 5 left. Okay, and so now we have finished that third diagonal. Okay, and we go to the fourth diagonal, which is here, and we're going to look at filling the 3P section, third ring, P section, and we know the P section can hold 6, but I've only got 5 electrons remaining to place. And this is one of the spots that students get into trouble. No, I shouldn't say trouble, cause an error, is because they go ahead and put 6 electrons because the section can hold 6 electrons. Okay, but you don't want to do that. I've only got 5 electrons left, so I can only place 5. So it's just like if you go to a ball game and a section can hold, we'll say, 1,000 people, and a row in that section can hold 25. Okay, so people buy their tickets, they come to the game, they sit down, but the row can hold 25, but if there's only 23 in there, okay, you don't just say there's 25 or add people. Okay, they didn't buy that ticket, so they can't sit there. So only put the amount of electron that you actually have. Don't fill it on your shell based on what it can have, because if we did that, then we would fill them all exactly the same and fill them all the way in, because they can hold that many. So I've got 5 left. I'm in the third row, the P section. So we'll put these 5 down here. And now we've drawn chlorine electron arrangement, electron configuration using the diagonal diagram, but we also followed along, and I didn't square these as I went to them, just this linear list of placement. So it doesn't matter to me which one that you use, you get to the same spot. This isn't a chemistry class by any means. For the most part, you're probably not headed to a chemistry field. So just understanding and being able to complete is good enough for us. So let's do one more just to see this. So let me get the eraser here, and we'll erase all these, and we'll erase my numbers, and we'll pick one just a little bit more going on so you can see a little bit more of the steps, go a little bit further. So let me clear this out so I can move this. So looking at the periodic table, I don't know, let's just pick, we'll pick krypton here. Trying to write on it, we'll pick krypton here. Oh, and I got the eraser selected, so that didn't work. So we'll pick krypton. It's got 36 electrons to place. So let me close this, not move that. All right, so let me get the diagram where it can be fully seen up here. All right, so now I've got 36. So I'm going to start a little bit higher. So I'll put my 36 up here. So we're doing krypton. Okay, so we know we got to do 1s. So we'll put those 2 right there. And I will be going probably a little bit faster just to get this through the process. And that completes that row. So now we go to 2s. Okay. And of course, once you do this enough times, you realize that right off the bat, you're going to place those 4. And then you really understand that right off the bat, you'll go 1s, 2s, 2p, 3s, 2p, 3p. And so as you have enough electrons, you will just automatically know where to fill those in, because that's pretty much right in order, and even throw in the 4 right in order. So we've done the first 4. We've got 32. So now we're to 2p. So we're going to come down here. And I'm just going to 5, 6. So now I've got 26 left. And that's the 2p, then the 3s. Now we're down to 24. Okay, and you may be thinking, man, this is going to take forever. But eventually the numbers start getting bigger, and so you subtract more as you go. So we did the 2p and the 3s, so now we're to 3p. So now we're going down here for 6. Now we're down to 18. Okay, and now we're doing the 4s. And once we get to the 4th row, we've got to understand that it's got 4 sections. So we've really got to go, basically at the top, 3 o'clock, 6 o'clock, 9 o'clock to have room for all 4 sections. But let me subtract my 2 here. Now I'm at 16. And now I'm doing the 3D. So I've got to come over here. Come over here. And I got to get 10, because D can hold 10 sections. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And because it's getting so close, I'll come back up here for 10. And that leaves me 6. Okay, and then I go to the 4p section. Okay, and this is also why I picked Krypton as well. So now I got to go to the 4p. And so 1, 2, 3, 4, 5, 6. And then we're done. And then you'll notice that Krypton on its outer shell has 6 down here and then 2 up here for 8. Okay, it has 8 electrons on its outer shell. So that shell, okay, from a bonding standpoint, would be considered full. Now, we are going to be adding more if we did have more, but we don't. Okay, and so therefore, based on the octet rule, the idea of 8, Krypton is considered to have a full outer shell. And because it has a full outer shell, it can't bond with anybody, because it can't take or share electrons. And once we get into bonding, that'll make more sense. But that's also why, and let me close this, that Krypton, no, I can't go there. Krypton is in this last row, okay? Because when you're in this last row, it should be these 1, 2, 3, 4, 5, 6 elements, your outer shell is considered full, or your valence shell is considered full. And you may be saying, what valence? What are you talking about there? Okay, so the word valence in a chemistry setting, if you were a home interior decorator, the word valence means a whole different thing. But in a chemistry setting, valence simply refers to the word outer. So the valence shell is the outer shell, or valence electrons are electrons on the outer shell. So that word valence simply refers to outer. So if I say, hey, draw the valence electrons for chlorine, you would draw the electrons on the outer shell. Now, another cool thing about the periodic table that's going to kind of lead us into our discussion of our first type of bond, which is ionic bonds. Let me scoot this. Need to see that picture. All right, maybe I'll move this picture. No, I'll just go over there and look at that picture because I need this space here for my examples. All right. The periodic table, as it's constructed, it has a lot of components and a lot of complexity. When we get into class, we'll actually fold a periodic table to show this. But there are generally two sections. There's the A section, which includes the first 2 rows and the last 6 rows. Okay. Then there's the B section, which is the entire thing. Okay. And you may ask, well, what's the difference? This section in here, I did it again, and it won't be the last time. This section in here are the metals. Okay, and they have their own type of bonding, the metal bonds and things like that. And you may say to yourself, what about aluminum here? It's a metal, but think about it as a metal. It's a really soft metal. So it has more characteristics of the things in this area than it does actually with the metal. So when we work with our periodic table in the classroom, we're going to take this section out. And the way you do that is you fold this section in such a way to where you can bring these 2 rows over to the other one. But we'll look at that when we happen. But you just fold it, and you can bring those 2 together, and you can tape it or whatever, and it kind of holds in place. But it's called a foldable periodic table, or you fold the periodic table to eliminate the metals so you don't have to look at them during ionic bonds and covalent bonds discussion. Now, the cool thing about the A portion of the periodic table is based on what column you're in is the number of valence electrons that you have. So if you're in this first column that I put the number 1 above, all of these valence electrons, all of these atoms, I should say, if you drew out their configurations or their electron placements on their outer shell, they would end up with 1 electron. Okay. Now the rings will vary. So in this case, hydrogen will have 1, because it's in that first column, electron on the first ring. Lithium will have 1 electron, but it'll be on the second ring. Sodium will have 1 electron on the third ring. Potassium will have 1 electron on the fourth ring, and so on and so on and so on. Same thing with the second column. Beryllium will have 2 valence electrons on the second ring. Magnesium, 2 valence electrons on the third ring. Calcium, 2 valence electrons on the fourth ring, and so on and so on and so on. And as we go along the numbers, it always is the same. Oxygen, 6 valence electrons on the second ring. Sulfur, 6 valence electrons on the third ring. And you can kind of keep that pattern going. So right away, when I say to you, hey, let's draw the valence electrons for arsenic. And I think this is arsenic right here, but it's kind of fuzzy. But anyway, you would know that, okay, it's going to have 5 valence electrons on the fourth ring, just by its placement of the periodic table. So you may say that, boy, this is really a long process, But in reality, when you're just focused on the valence electrons, it's pretty quick to recognize how many it has and where they are as far as a valence setting. So we've got 3 types of bonds to look at and in the rest of our section, and then we'll be done for the day. Ionic bonds, covalent bonds, and hydrogen bonds. Now, and again, hopefully if you've had chemistry, you're going, yeah, I got this. We've spent a lot of time on this. Ionic bonds, I'll get a quick drink here. Ionic bonds, covalent bonds, you can think of them as being the opposites of what they do with the electrons. An ionic bond, as you can see here, and now I'm reading from up here. Ionic bond is a bond between a cation and an anion. And the end product is that an electron is going to be taken. If you remember our talk from last time, this is the cation section, and this is the anion section. And hopefully right away you're saying, yep, I got that. Anions, stronger, powerful. They're the ones that are going to be taking electrons. Cations, gentle, soft, they're going to be the ones losing the electrons. Okay, and I also have a little note here that the octet rule, the needs for the octet rule, kind of creates compounds or molecules based on the ionic bond partnership. But we'll talk about that with some examples. So let's take the old common example of water. Okay, so if we work with oxygen here, okay, we know oxygen has 6 electrons on its outer ring. So if I were to draw an oxygen atom, put a little O in here so you know it's oxygen, it's going to have 6 electrons. So 1, 3, 4, 5, 6. These probably should be a little bit bigger here. All right, those 6. So if it needs to meet the octet rule and it's got 6, mental math tells you that it needs 2 more. It's got to get to 8 somehow so it can have a full outer shell. So what it does, it's going to create an ionic bond with somebody over here to meet that rule. Now, if it took, for example, if it bonded with the beryllium or anybody in this second column, that would, and it would take those electrons, that would give it its 8, okay, to be full, okay. But we're going to draw a water. So what I'm going to do here is I'm going to draw a hydrogen atom, and it's got 1. Here's another hydrogen atom, and it's got 1. So when these 2 hydrogens bond with this oxygen, not only do they make a molecule of water, it's easy for me to say, but what happens is that now, because these 2 additional hydrogens have been added to the oxygen, it has a full outer shell, okay, because it's got 8. So that's the idea of what we're trying to look at here. So let's look at another example. Salt, sodium and chlorine. So if I come over here, let's change colors, and I draw me a Cl, chlorine, which is right here. We know that it's got 7 valence electrons on its outer shell. 4, 5, 6, 7. And again, I didn't space these out very well, just trying to show you the concept here. Now, right away, you should be thinking, okay, chlorine needs 1. So the question is, can a chlorine molecule ever bond with somebody from the second row? An ionic bond where it's going to take its valence electrons. Hopefully you're saying, well, no, it can't, because then it would have 9. Okay, and that wouldn't work. So a chlorine atom will not bond with somebody from the second row. When it's going to make a bond, it's going to be with somebody from this first row over here. And the most common one is sodium, okay, to get that NaCl or to get salts. So now I've got this sodium. And what's going to happen is, because chlorine is so much stronger, this electron is going to be taken. And then chlorine will have 8. And then the magical thing that happens with sodium is, because it loses that outer electron of 1, that outer ring, or in another case, the third ring, just disappears, because, as I mentioned earlier, there's no electrons on it, so it's not observable. And so that means now lithium or sodium has 2 rings. Okay, and now its outer ring, which is that second ring, would be considered full, because it's got that, the S section of the second ring is full, and that section is full, so the ring would be considered full. So what happens is, as you reach those outer shells being full by gaining electrons to build up, but you can also be considered full by dropping down a ring, because you lose all your valence electrons. And of course, let me close my ink pen here. And when I say take, if you think about it, this is a tug of war. Okay, on this side, if you've gone through a physical science class, maybe you've seen this. This is a screenshot from simulations, but it's the balance force simulation. This side has much more force being applied to it than this side. And in a tug of war, this wagon is going to go this way, because there's more force on this side, and the wagon eventually goes all the way over to the red side. That's how tug of war works, as you know. And that's, so an ionic bond is a reference to a difference in power, okay, and taking of those electrons, with the idea of the anion gaining electrons to fill its outer shell, okay, and the cation losing electrons and dropping down to a full shell. So let me close this so I can move us down to here, and so we can talk about our last several topics. Now, everything that we're talking about is, and let me go down just a little bit, because I got to draw on this periodic table here. Everything that we're talking about is the idea of electronegativity. Okay, electronegativity is this reference to how well an element can pull on electrons. Okay, is it a super strong element that's going to take the electron? Is it a very weak element that can't hold on to its electrons very well, and therefore loses the electron? If you play sports at all, especially football, a metaphor that you could use to think about this is the way a running back or receiver, or somebody who's running with the football, even if it's a quarterback who's decided to scramble, how closely, or the proper way of holding the football, trying to reduce the opportunity of fumbling it. And if you've been involved in football, whatever, it's a 3-point process, to where the football is against your ribs. It's under the one tip is under your, just lost my word for the space underneath your armpit. And then the other spot is the hand is over the other end. And by doing those 3 points, you try to reduce the possibility of fumbling the football when you're hit or tackled. So if a football player holds the football out away from himself and he's running, he has a greater chance of fumbling than when he has it tight up against his body in that manner. Just like if a person just had it in their hand, like they're palming a basketball, running with the football, more likely to fumble. Electronegativity refers to how strongly an element can pull on or hold on to electrons. And the way this works is that, get a pen here, as you go from left to right, okay, the elements get stronger. So I'm going to put a plus sign and then a negative sign. It's not plus or minus. This is weaker, stronger. Okay. Same way as you go up. As you go up the periodic table, weaker, stronger. So what that means, let me pick a different color. Let's go green. That means that this section, this corner up here, are the strongest electrons when it comes to electronegativity. That also means then that this corner would be the weakest. So we're going to put a big old S here. We're going to put a W here. Okay, the weakest of the two. So as you go left to right, it gets stronger. As you go up, it gets stronger. So when oxygen or fluorine comes around to create an ionic bond, the cations really don't have much chance because those are some of the strongest elements that are out there. And if you're a franconium here in this corner down here, okay, you're really in trouble because you're the weakest element. And when the fluorine comes along, I mean, it's just like, pardon the expression, taking candy from a baby. They just reach in and take those electrons, easy peasy. So that's an ionic bond. Cations, anions, taking electrons, losing electrons. And yesterday we mentioned ions. I shouldn't say yesterday. The last time we mentioned ions. So let's draw that word ions here. Okay. So when oxygen takes an electron, okay, so in oxygen, it has 8 protons, 8 electrons, and then we'll just pick lithium over here. Lithium has 3 protons, 3 electrons. All right, and so when they bond, ionic bond, and one of these electrons is taken and goes over to oxygen, now oxygen has 9 electrons and 8 protons. So since it has more electrons than it does protons, it's now labeled with a minus sign or a negative ion. Lithium, the opposite, has 3 protons and 2 electrons, so it has more positives than it does negative, so it gets a plus sign. And that's ions. Oxygen would now be a negative ion, and lithium would be a positive ion because it has more or less of the electrons than it does the protons. So that's a tie-in back to last time, our discussion of ions and what it looks like in this setting. So that's ionic bonds. Let me close my chart here so I can move this up. Bring my pins back up. Back to the blue. So now we're going to talk about covalent bonds. And covalent bonds, as you can think about as compared to ionic. Excuse me, I'm going to drink here. As being the opposite. because the electrons are shared. And shared is kind of a not a great descriptive word of what's happening, because the elements they don't want to share them, but similar to, and let me close this out and let's go just a little bit bigger so we can see this diagram a little better. Okay, and it's kind of fuzzy because it's really small for some reason. But if we look at this diagram here, and we're looking at this one right here, and it's kind of hard to see, but this is a balanced tug of war. These two guys are the same strength level. Now, when we hit this go button, they both begin to pull and pull and pull, but because of the same strength, the wagon doesn't move, and nobody wins the tug of war. So the electrons in a covalent bond are considered shared. Now, both elements are pulling on them, but if they are the same strength, then the electron doesn't go anywhere. It stays where it was. So if I take, now covalent bonds are also, for the most part, bonds between elements that are the same. In other words, they're a gas, like oxygen gas, nitrogen gas, chlorine gas, whatever you would call it, whatever you want to think of. So you would have two oxygens, which would obviously be the same strength, and so you're pulling on the same, so the electrons would stay where they were, or two nitrogens, nitrogen gas. Okay, you can't have covalent bonds amongst other elements that are not the same, but from a percentage standpoint, for the most part, they are two that are the same and they form gases. Okay, but when they're not the same, well, I shouldn't say that. It can happen amongst the two. But covalent bonds, when they do bond, to help with the octet rule, they use single, double, or triple bonds to fulfill that octet rule. So what I mean by that is, let's look at, and you can kind of just tell, let me close out my ink tray here and move back up to this periodic table. That worked. All right, so if I've got two oxygens, okay, and they're going to bond to form a covalent bond, and they are going to meet the octet rule, they each need two. So what they will do is create a double bond, okay, and in each of those bonds would count towards each atom. So you would have my 6 plus your 2 that we bond with, because of double bond, that would make 8. And then the other one would be like, okay, I got my 6 plus your 2, that makes 8. So let me go back up here where I got some room, and we'll draw that just so it makes more sense. So if I've got an oxygen and another oxygen, okay, and we know they've got 6. And then 6 over here. So they need 2. So what's going to happen is, let me pick a different color here to showcase the bond. They're going to bond here, and they're going to bond here. And now you can count your 6 plus the other 2 to come up with 8 as far as you're meeting the octet rule. Okay, so but if you think about that, and again, both of these bonds, ionic and covalent, we will use the models and the drawings time and time again to make sure that you can grasp this scenario. So if you think about nitrogen needs 3. It's got 5. So if it bonds with another nitrogen, it would use a triple bond to meet the octet rule. Okay, just like with the oxygen. So if we come down here and we draw a couple of nitrogens, And they've got 7, 4, 5, 6, 7, and 7 over here. No, I did that wrong. I was going to say that's not making sense. It should have just been 5. So let's start this over again. Because as soon as I drew those, I was like, wait a minute, that isn't right. Should have been 5. Right? Let me go back up and show you that. I misdrew there. We should have been 5. So 1, 2, 3, 4, 5. And then another nitrogen over here, 5. All right, so I've got 5. I need 8. So we're going to come, let me do a different color here. We're going to bond here. And we're going to bond here. And we're going to bond there. And now I get to count my 5 and your 3 to make 8 in the octet rule. Okay, so that's the idea of covalent bonds, sharing, but not really sharing out of want to share. We just are the similar strength, so therefore neither one of us can take the other away from each other. Now, so we got 2 topics left, and they're fairly short, fairly straightforward, but super, super, super important, and they're going to lead us into our next discussion the next time, and that's the properties of water. Okay, our next bond to talk about is hydrogen bonds. Okay, hydrogen bonds are super, super, super special bonds that really allow us to even be alive, okay, and to function in a proper manner, an efficient manner. Now, you may think that hydrogen bonds, okay, that's bond between hydrogens. No. Hydrogen bonds are, let me get a pen here so I can showcase one right here. We'll just focus on this component right here. Hydrogen bonds are between a hydrogen atom and the main atom of another molecule. So for this case, obviously this is a bunch of water molecules. So this hydrogen is bonding with this oxygen. And this oxygen, hydrogen, that's a hydrogen bond here. And if there were another water molecule out here, then this hydrogen would bond with that oxygen. So a hydrogen bond is a bond between a hydrogen atom of one molecule and the main molecule of another, the main element of another molecule. That is a hydrogen bond. And because water does that, it creates so many special properties. Right off the bat, you can think about surface tension. Okay. So, but we'll talk about the properties of water in our next video lecture. But hydrogen bonds are pretty special because they happen in almost every important molecule that's in our body. Think about all our macromolecules, our carbohydrates, our proteins, our lipids, all that stuff, our DNA are held together by hydrogen bonds. And hydrogen bonds are special in such a way that they're not bonds that are very solid, strong bonds. They are kind of like those refrigerator magnets you put on your refrigerator that can hold a paper or two, but if you put too many papers, they start to slide down. That's the kind of magnet you want to think about when you think about a hydrogen bond. But there's a reason for that. Hydrogen bonds can be taken apart and put together very easily. Okay, if you had to every day change, maybe it's a lunch schedule, maybe it's a who knows what, baseball schedule, but every day you had to change this piece of paper from the refrigerator, you wouldn't want a super strong magnet. You got to really struggle to get it off the refrigerator. Hydrogen bonds can be taken apart easily, put back together, and one area that's super important in is our DNA being replicated or copied, which happens in the cell cycle constantly all day long. Our DNA is held together by hydrogen bonds, but that allows us to take it apart easily, copy it, and put it back together easily. If it was a strong covalent bond, it would take a lot of energy to break that bond, and your body would need to recoup that energy from somewhere. It would take away from other areas that need energy as well. Only so much energy in your body, and if you had to use more to separate the bonds, you'd have less for other places. So our last topic to talk about, and that's going to be right here, okay, the idea of polar. Now, we said covalent bonds are bonds where they share, okay, but we also talked about electronegativity being a measure of how strongly an element can hold the electrons. So we're going to scroll back up here. Okay, I mentioned that the electronegativity increases as I go up and increases as I go over. So what you'd have to think about is that as I go across left to right, okay, each element to the right is a little bit stronger, okay, not strong enough to overtake in a tug of war or win a tug of war, but it is a little bit stronger. Okay, so fluorine is just slightly stronger than oxygen. Oxygen is slightly stronger than nitrogen, and going up the same way. Xenon or krypton is a little stronger than xenon. Argon a little stronger than krypton, and so on and so on. So if you think about, let me move this back down here so I can get some space here. So if you think about a covalent bond, I got this is the rope, okay, and I got somebody over here, and I got somebody over here. Now, they are almost identically the same strength. So if I've got this red flag here in the middle, that's the red flag in the middle, and the tug of war, you would try to pull it to either side. So, but just say that this person over here, and we're going to label this person with a negative sign, and that's on purpose, a positive sign. And remember, this is an electron, which is a negative. Okay, so this person over here is just slightly stronger, and they pull that flag or that electron just slightly towards them. Just slightly. I mean, just if you're measuring it, if say the rope is 10 feet long, maybe they move it 4 or 5 inches towards them, and that's it. Okay, but because that happened, we now have created a negative end of the rope and a positive end of the rope, because this end of the rope has more electrons and protons, and this end of the rope has more protons and electrons. That is a polar molecule. Okay, this is a water molecule, oxygen, 2 hydrogens. Now, they're relatively the same strength, okay, but the oxygen is a little bit stronger, and so it pulls those hydrogen electrons just slightly towards it. And when it does that, it creates a negative end of the molecule and a positive end of the molecule, just like the rope example over here. So a polar covalent bond is simply the idea that one element is just slightly stronger and has pulled the electrons just slightly towards it, just like a slightly stronger person pulled the flag or the electron just a few inches, just a little bit closer to it, and therefore made a negative end of the rope and a positive end of the rope. That's the same idea over here. So hopefully that gives you a good idea of the different kind of bonds, what's happening, why it's happening, what it looks like, and with the idea of once we get in the classroom using paper and pencil and the ball stick models, we will practice trying to drive home these concepts. So again, thank you for tuning in. Thank you for watching this. And I hope it was enjoyable. I hope you can pick up on the importance and the enthusiasm and the excitement that this stuff could bring. Just this information right here, man, you could go out and you could study this stuff and a career and just have all kinds of opportunities just from this information. So again, thank you. Appreciate everybody for tuning in. Appreciate the hard work and the notes that you took. And I look forward to seeing you in class where we can put some hands-on, some models, and really have a lot of fun with this stuff. See you till next time.